video, I'll continue talking about both the sequential and graphical methods of calculating limits, just kind of expounding on what I've said already. So to begin, what if you had a table of x and corresponding f of x values like here? What can we say about limits? Well, it appears that the x values are going to 1 from the left, so we could say that this is telling us about the limit as x goes to 1 from the left of f of x. And if we check the corresponding f of x values, they appear to go to 2. So hence, this number is equal to 2. Now we can say some more about the graphical method, choosing a slightly more complicated example. So here is my f of x. All of this is f of x. And if I wanted to talk about the limit as x approaches 0 from either the left or the right, they both seem to be 1.5. And in fact, the value of the function at 0 is equal to 1.5. So that's boring. And in fact, that's an example of what we call continuity. That's basically when the limits and the value of the function agree. I'll make another video next about that topic, but for right now, we'll just regard that as boring and ask about more interesting points. So let's take, for example, x equals -5. Could we say what the limit is as x approaches -5, assuming that this is the full graph of the function and that it doesn't exist off the page anywhere? Well, no, we can't, because we cannot plug in x values to the left of -5. The function isn't defined there, so we can't see any limiting behavior. But we can find the value, the limit, as x approaches -5 from the right. And if we do, we see that the y values get closer and closer to 0. So the limit is 0 as x approaches -5 from the right. What about as x approaches -3 from the left? It appears to approach 4 on the y-axis. What about as x approaches -3 from the right? Then it appears to approach -1 on the y-axis. Here's a question. What is the value of the function at -3? Well, we can't use the limits because they tell us two different things, but we are typically signaled by a closed dot to tell us where the function exists at these unusual points. And here I have a closed dot on the endpoint over here, so the value of the function at -3 appears to be -1. I could write that. If I were writing this on paper, I might say f of -3 equals -1. So that's the value of the function at the point. Now, throughout the rest of the curve here, it's boring, but as I approach 1 from the left, the value appears to be 2.5, but the limit from the right is 0. And if I plug in the point, I have a closed dot here telling me that f of 1 is equal to 1. So in fact, here's an example where no three of these quantities agree. And in general, whenever you're doing these problems, you want to keep track of these three important quantities at every point: the limit from the left, the limit from the right, and the value of the function at the point. So we can also take another example, like 1 over x, where the limits seem to fly off to infinity, and they do. We call those vertical asymptotes. So as x approaches 0 from the right, the value of the function just goes to infinity, and therefore the limit does not exist. And if we approach from the left, then the value goes to -infinity, and again, the limit does not exist, nor does the value of the function. So none of those exist in this case at 0. Although anywhere else it's boring, right? The value and the limit at 1 is equal to 1. So in general, we like to know where these asymptotes are located and what the limits are from the left and the right. I can take this more complicated example, graphed like this, and if you'd like to see the written function, it's this. And we can say from the left, the limit as x approaches -2 is infinity. From the right, it's -infinity. You can't really see it easily from the graph, but down here you can tell that the limit as x approaches 0 from the left is going to get us a vertical asymptote because of the 0 in the bottom of this rational function. and there's no corresponding anything up here to cancel it. So there has to be an asymptote here, and it goes to infinity from both the left and the right. If we approach if we approach 2 from the left, we get negative infinity, and if we approach from the right, we get positive infinity. So there you have it. This is generally the graphical method of finding limits.